So today I'll talk about structure and function. You heard a beautiful talk. I'm biased, but a good talk by Antoine Légaré this morning about the structure function relationship. And of course, oops, it doesn't change. Maybe it's not.
Maybe it has to focus.
Yeah. We heard about structure function relationship. And as you know, it's essentially based on two questions. How much the structure, that is a connection between the parts of the brain or between the neurons, determine the function, the activity of the parts of the brain. And how much also, when you observe the activity of the brain or some parts, can you guess what is the structure? It's a very tough problem. It has been studied a lot in the last 2 decades, especially in the last decades, thanks to network science, who emerged also as a dominant science in neuroscience approach. And if I may recall a little bit, typically what you have is you have two sides of the story. One is the structure, the set of connection between neurons and parts of the brains, and you can construct a connectivity matrix from this. And on the other side, you have dynamical observation, the activity levels of neurons or part of the brain. And typically, you compute one statistics, correlation, say, and then you build a correlation matrix, and you can compare those two and see if they are correlated. And typically, you would see beautiful correlation that's around 0.5, sometimes 0.6 or 7. And one question we can ask is it that good? Can it be better? Higher? Is there a theoretical limit? And this is not so easy to answer this question because there are so many methods. If you look at the problem of inferring the structure from the function, there exists literally dozens of methods of statistics that can be used. And the problem essentially is, Antoine summarized it this morning, is when you compute, for instance, correlation, almost all the parts of the brain are correlated on neurons because they are indirect connection between them. So one of the big tasks is, okay, can we get rid of this indirect connection? And this is based on causality detection. There are methods like Ranger causality, transfer entropy, causality in climate science, etc. So many methods that can be used to infer the structure. This is one side of the story. And when you look at all the papers, you realize that, okay, this is a very difficult problem. And there's more, because there's degeneracy. So we know in neuroscience since 20 years ago, thanks to Yves Marder and collaborators, that you can have a very simple neuronal network with 3 to 12 neurons that are connected together. And if you change the connections, the weights of the connections, you can produce always sometimes the same output, the desired muscle movement that you want to have. So there's no unique solution. In other words, the problem of looking at the structure and say, and looking at the function and say, okay, I would like to find the connection pattern between the neuron that can explain this activity is ill-defined. There are many solutions. And in network science, it was studied a lot. And people recently realized that you can have very different topology, that is patterns of connections that produce also for different kind of dynamics, not neuronal, it can produce the same dynamics. And especially this problem is related to the fact that this dynamics, the activity of the nodes in the networks, propagate on a low dimensional space. So today, I'd like to look at these problems, take a step back and answer essentially 4 questions. So how should we measure the structure-function relationship? I can give one answer, a very specific one. And is there any theoretical limit between the coupling or the coupling between the structure and the function? And how the connection between the neurons can constrain the activity of the neurons, and this constraint does it have an impact on the dimensionality of the space covered by the activity of the brains? And to answer that, I will use two papers that was recently published in our group. And I'm very happy to present these papers here today because actually these two projects started up as final project in graduate courses. One in information theory, and Charles started up a project and said we should apply information theory to the problem of structure and function. And the other one started up in a course about a spectral graph theory, and you will see why it's related. So let's start with the first paper by Charles and I. And in this paper, we use information theory. And for this, we want to measure the link between the structure and function. And it's only possible in information theory if you use a trick. You need random graph and a stochastic neuronal. So here, it's not based on data at all. It's all theoretical. So what do I mean by random graph? So it's only a set of graphs. Here's one. In here, each node represents probably a neuron and a link, a connection between the neurons. And it's a set of graphs with probabilities. So in this case, I have 4 possible graphs, and they all have the same probability. This is the typical picture you have when you think about a random graph. But some of them can have different higher probabilities. So if you look at this one, you can see that if you have like modules, it's higher, the probability is higher. And if you have only one, the probability is lower. And actually, you have so much possibility to build a random graph. It's well known in classical books of graphs and network science. In neuroscience, we use a lot of stochastic block models that are useful to generate artificial network with modules inside, with densely connected modules. And you can also have more sophisticated model, like in this Berzel paper, which is one of the first papers where you have more realistic models of random graph, but that generates something that is a random brain, essentially. Okay, this is one type of the story, random graph. And now I need a stochastic neuronal activity. So typically what you need to do when you select the stochastic neuronal activity, you pick randomly a graph, the first one here, and then you propagate a dynamics. Here, the yellow or orange means that the neuron is active, fires an action potential, and the blue one means it's non-active. And because it's random, this is the first time step, and the second time step, it could be the same state, but then you can activate more neurons. And at the end, you get a matrix in which rows represent the neurons and columns the time steps. And this is one possibility. But of course, because it's random, you can have other possibilities of evolution. So you start with the same initial condition, but then the transition are random. And the probability at the end, it's what defines the activity model. So how can we define an activity model? Stochastic, there are like 2 big classes of activity models that are used in computer neuroscience or in mathematical neuroscience. Typically, you have the stochastic differential equation, mainly used by Brunel and collaborators, in which you consider the membrane potential for each neuron, and you have stochastic inputs. So it's a noisy differential equation. And you have also more basic Markov chains possibility. So because we needed to extract analytical results, the second family is more complicated. So we decided to use the Markov chains that were used, for instance, in the 70s by Wilson and Cohen. So some of you may know the Wilson-Cohen model, which is very important to explain the oscillation behaviors in the brain. But if you read carefully the paper, at the beginning, the hypothesis is really a Markov chain. And what you know as differential equations this is the mean field approximation of this. So now we decided to use a binary Markov chain as a simple model. So here X represents the activity of the neurons. X1 is the random variables that encodes all the activity of each neuron at time 1 until time step T. T is important because I will use it later. When we define the model, we need to have the Markov property, which only says that when you do a transition from one step to another, the second step depends only on the first one and not on past events. And then you can define more the activation like this one, the probability transition between a state of all the neurons from time T to the next time steps. And typically in this equation, I know it's a bit long, you have the number of neurons, you have the activation probability of neuron I at time T, and then you have the deactivation probability at time T. You have a lot of freedom in that equation to choose, and you have other parameters, M and N. So M is the number of active neighbors or presynaptic neurons, and N is the number of inactive presynaptic neurons that can influence the activity of neuron I. And in the simplest case, and this is the one I will present today, you can choose the activation. Many of you will recognize here a sigmoid activation function. And you have one parameter here, the coupling, which is okay, what is the synaptic strength between the presynaptic and the postsynaptic node. And you can have the deactivation probability that could be non-constant, but in this case, I would always take 0.5 just to simplify the notation and keep only one. So now we have the random graphs, we have the random activity, so we can use information theory. So on the one side, you have this structure that is random. The other side, you have also the activity that is random. And in information theory, you use that kind of diagrams to represent the uncertainty or the entropy. So the fundamental quantity here is H. H is a measure of unpredictability about a random variable. So imagine that you have a large entropy. It would mean that you have no clue about what is the graph you will pick. On the opposite, if you have low entropy, it means that you have no surprise. You pick maybe one or two graphs and they have high probability. The same is true for the activity. So H, which is measured in bits, is the uncertainty, how much you can, how easy is it to predict the value or the time evolution of your process. If it's unpredictable, then the entropy is high. If it's easy to predict, the entropy is low. And you can also compute this as the number of yes/no questions you need just to determine the value of the process. So the entropy here is represented by the big circle. So it's the uncertainty you have. If the circle is big, you have a big uncertainty. If the circle is small, you have a small uncertainty, and that's the same. And between, you have what is called the mutual information, which is defined using conditional entropy. But I will not go there. I just need to say that this represents the number of bits that the random graph and the random activity share together. It's the quantity of information that they have in common. And so using only basic information theory, you have a measure of structure and function relationship that is objective, that doesn't depend on any algorithm, and it could be applied in principle to get numbers to quantify this relationship. Okay, although it's very tempting, it has a problem. So yeah, there are scenarios in which you can have a lot of uncertainty about the structure. So in this case, you would have what we call weakly reconstructible. So it's very difficult to guess what is the network that is responsible for the activity. And you have, in this case, a very small uncertainty about the dynamics, so it's highly predictable. And on the other side, for the same quantity of information, mutual information, you have a case where it's highly reconstructible because you have a low uncertainty here, and weakly predictable because you have a lot of uncertainty about the dynamics. So to get rid of that problem of normalization, we define uncertainty coefficients, one for measuring the predictability and the other one for measuring the reconstructability. So it's how much is it easy to predict the dynamics when I know the graph, and how much it is easy to predict what is a graph when I know the dynamics. And these measures are bounded between 0 and 1. So if you have a value of 1, you can predict perfectly the evolution when you know the graph. And also when you have reconstructability of 1, it means that if you observe the activity, you can guess what is the graph that is responsible for that activity. So this is theory, and we compare that to known measure in network science, just to study predictability and reconstructability. So for instance, here we have the problem of reconstructability. You look at the activity of your network and you want to guess what is the network. And you can use basic statistics like correlation here. That's not very good. And you have other like Granger causality or transfer entropy that gives a good performance. But all that is to say that even though it's theoretical, in principle, it also captures the shape, the behavior of the algorithms. So what we got a little surprise. So with information theory, we can measure the structure and the function relationship, but also we unified reconstructability and predictability. And we observe a new phenomenon, which is a duality. So it means here I have a very cartoon representation where I have only 2 possible graphs and 3 possible time series, and with 2 parameters, R and S, which are probabilities to generate this time series, probabilities to generate this one. But this is enough to show what's happening. So in the case where S is equal to 1, this is not possible, you see that predictability and reconstructability, they grow together if you change the probability part. But if you pose that this probability is non-zero, then you get something different in which the predictability can decrease while the reconstructability will increase. And this is what we call a duality. So even though they are related by mutual information, they are domains of parameters in which we have a dual behavior. And this has been tested on larger network of models of neurons. On the top, you have the common model, the easy one, on a random graph with no data behind it. And on the bottom, you have the simulations for the case of the C against the connector. And here it's a bit complicated because if you do the random evolution of neurons, they always fire, but they tend to stabilize at some firing rate. And typically what you have is a branch of high activity of some neurons and a branch of low activity of neurons. And it's possible to go from one branch to another if you change the gain, which is written by nu here. So if you change the gain, you have a phase transition from one level of activity to the other. And if you look at this, you have 2 critical lines. They are reproduced here. And close to these 2 critical lines, this is where you get the best predictability. You see the maximum here, although the values are very weak, very low. And after these critical points, you get the best reconstructability. Here in the random network, you have something that goes up to 60%. And in the case of the C elegans, you have something that goes up until 3%. You have this zone. What we don't see it is in gray, where predictability decreases while reconstructability increases. So this is a general phenomenon. And actually, we observed it that if you take the parameter to be the time, you will always get that kind of duality. And we have a theorem about this in the paper. And of course, you can also make things more complicated. You can say, okay, I have information not only about the structure, but also about the past of what happened in the neuronal network. You can define your new quantity and you still observe this dual behavior. So if I summarize the first part, I'd say that mutual information can serve as a measure of structure-function relationship in the case where you have both random graph and random evolution. The uncertainty coefficients allow you to predict your capacity to reconstruct a graph or to predict the evolution. These two measures, although they come from mutual information, they can have dual behavior, and duality seems to be related to criticality, phase transition. And there's one duality that is always there. This is the one that's related to the number of time steps. So this is the end of the first part. Am I late? It's fine. The second part. So again, related to a project in a graduate course. This was motivated by a long tradition in our group to study dimensionality reduction. That is, if you have a very complex systems with lots of equations, you try to find a way to reduce the dimension of this. And you base your analysis on the properties of the networks behind this. But we always wonder, is it always allowed to do that? Another motivation is the dimensionality of neuronal activity. Here I have a cartoon in which on one axis I have the firing rate of one neuron, the firing rate of a second neuron. So we have two typical cases. A case where neurons are not correlated. So if their activity evolves, they will span a surface, a 2D manifold. And in this case, if they are strongly correlated, their time evolution will span a one-dimensional manifold. And you can, of course, represent the same case for three neurons, in which we have one dimension, two dimensions possible, and three dimensions. And as soon as you have more than three neurons, it's impossible to represent. You have a problem of high dimensionality. But we expect, due to the previous studies, that as the number of neurons grows, you should have a smaller dimension for your manifold. And why? It's because, for instance, in these papers, in Gao and Ganguly work, they show that in many studies, you also always observe that the number of dimensions you need to explain most of the variance in your study is a very small fraction of the number of neurons. And other studies with a lot of neurons, thousands of neurons in a Carson strainer, they claim that they have a high dimensional geometry. But here, high dimensional is a question of dimension. In what follows, this high dimension becomes low dimensional. So we still agree, it's just a question of definition of what is high and what is low. So for our approach, we decided to use dynamical system theory. We always make an abstract idea of a neuronal network that is a graph with direction weights between the nodes. And to study the activity, we use a set of ordinary differential equations. So we're no longer here working with stochastic neurons. It's the case of deterministic, like Wilson-Cohen equation. So what is the low rank hypothesis that is mentioned in the title of the paper? So it says informally that the dynamics of the complex system, including neuronal networks, can be reduced to a few equations involving a low rank matrix describing them. And why we posit this hypothesis is because we realize that in the scientific paper, about neuronal networks, but also about dynamics on networks and networks in general, there's always that hypothesis that is made without any justification. So it says that in many models that you study, you always have a connection matrix that is made of a low rank matrix plus some noise. And if you don't like the idea of what is the rank of a matrix, I will define it right now. But that was our justification. And we checked that in many examples, this hypothesis is made. So let me say why we care about the matrix rank and how is it related to dimensional. So imagine that you have a connector. The biggest we have, the more precise is Drosophila, and it's with maybe 21,000 neurons. Of course, you can represent it as a network, and this can be represented as a matrix. But there's a trick in matrix linear algebra known as the singular value decomposition. It says that you have a matrix, you can write it as a product of three matrices, and the one in the middle is very important because it's diagonal, and the non-zero values on the diagonal are called the singular values. They are positive values, and usually they are ordered from the first, the biggest one, to the smallest. And this factorization allows you to do an approximation, low rank approximation. So the rank here is the number of non-zero parameter here. It has also another interpretation. Whoops, sorry. So this equation can be written as a sum, and it says, okay, this matrix network can be represented as the first term, which has the largest contribution, and till the last one are being the rank with the smallest contribution. So if you've done PCA in the past, without knowing, in general, you're doing singular value decomposition. These concepts are related. How is it related to dimension? The rank of the matrix is the dimension of the space generated by the product of the matrix and all possible vectors here. So if you go back to the models of neural network, in this case, X is the firing rate of all the neurons in the network. And this Wx will be the incoming activity to each neuron. So it says that if you have a low rank for this matrix, so a small number of non-zero values here, even though you have an initial space of states that is large, when you do the matrix projection, it goes to a very small space here. So this is for rank. If it's still too abstract, I have another interpretation. It's a beautiful observation that any kind of flags have low ranks. So if you take the flag of France, it has rank 1 because all the lines are equivalent, so the rows are equal. If you take the flag of England, it has rank 2. So it's a sum of a rank 1 matrix plus another rank 1 matrix. If you take a more complex flag, like the Nunavix flag, that is very beautiful in northern Quebec, it's not a sum of only 1 or 2 or 3, but it's a short sum of some matrices that give a good approximation. But it's not exact in the sense that each time you add a new matrix, then you get a better representation. But you still see regularity in that flag. So for very simple flags, you have a low rank. For this flag, although you have regularity, you have a higher rank, but you would like to describe this regularity here. And this means that you still need a better measure of dimensionality. And we don't use rank exactly, but that's something that is called effective rank. So if you go back to the singular values that were the elements on the diagonal matrix, you would say that a low effective rank is something that says that the singular value decreases a lot. And if you have a high effective rank, it's when the singular values decrease linearly or more than linearly. So more precisely, there are many measures of effective ranks, and there were a very recent development in linear algebra about this, especially thanks to the addition in Neuronal in the last decade. And they define new effective rank. So here I will give only one measure of effective rank that comes back 20 years ago, I think. But in general, the effective rank is the number of significant singular values in a matrix. And one example, the simplest one, is the stable rank, which is given by the sum of the singular value squared divided by the first value squared. The formula here is not important, but it captures that behavior. So if we go back to dimensionality, it means that if the effective rank measures the approximate dimension generated by all these products. So if I go back to the pictures I had before, I'm sorry. It means that if you have a low effective rank, when you do the product of, say, irony rates here and the connectivity matrix, it's possible that you do in a large space, but most of the values will live in a very small space. So you have a low dimension. So here I have typical singular value decreases possible. So if you take nodes, so neurons that are not connected, this is the case where you don't decrease at all. So this means high dimensionality. If you have a chain like this one, you have a decrease, but it's kind of a slow decrease. A grid, regular grid, you have a sharper decrease here. In the extreme case is a star like this one, in which you have one non-zero value and the other one are zero. So these are examples, and you can quantify this using asymptotic analysis to say n is the number of neurons or nodes in the networks. So if you look at these typical behaviors, you can have supralinear, linear, and something that is faster. We call them hypergeometric or exponential. And we define what is low. So low is faster than linear. And why it's low? It's because if you take the effective rank divided by the number of neurons, and you take the number of neurons that goes to infinity, this is going to be zero, negligible. So it's an objective criteria different. 1 minute. So now we have a more precise idea of what is the low rank hypothesis of complex systems on neuronal networks. It says that the network's weight matrices have rapidly decreasing singular values, implying effectivity. So this is a theoretical measure or idea. Is it true? So in real data, if you collect almost 700 types of real networks, biological, technological, you can compute the decrease of the singular value, and you realize that it does decrease rapidly with this typical shape that is sublinear. And it means that in most cases, the ratio between the effective rank divided by the number of nodes is always below 10%. So you always have something like a small space behind. If you do the same analysis, but this time with only the connectomes coming from neuroscience, you see that the decrease is even faster. And the best example is the Drosophila case, in which you have an extremely fast decrease of the singular values. You can also, there's a beautiful paper in which they studies the connectomes of developing C. elegans for many days. So it starts, many days, it starts from 3 hours after hatching to 2 days after hatching. And if you look at the connectomes they produce, you see a decrease in the singular values. It means a decrease of the dimensionality. And with this, we concluded that there is actually a low rank hypothesis in many complex systems. And with this, I won't go in more details about the math there. But once you have establish that you have this low rank hypothesis, you can start with your very complicated neuronal activity, project this into a lower space, evaluate the error you make when you do the projection, and then at the end, obtain a reduced system with lower dimension. And what is new, which will be no longer have a graph, but you have a micrograph. It means that when you lower the dimension, you don't have only pairwise interaction like between neurons, but you have interaction between triplets, quadruplets, etc. So it's more complicated. But you can do it and quantify the errors if you're interested. There are theorems in the paper. And if I go for the last conclusion, so the low rank hypothesis that was observed in the papers and the models is maybe not just an hypothesis, but something more like an intrinsic properties of the real complex systems. The real networks, and especially the connectomes, have low effective rank. The effective rank are often at a non-negligible fraction of n, like 10%. And this is a warning. So it means that you cannot use a too simplistic model in when you try to model neuronal networks. You have to take a rank that is high enough to have something that is more realistic. And large neuronal networks with a firing rate dynamics, that is with dynamical equation that are differential equations, ordinary differential equation can be reduced in dimension thanks to this property. And if you use PCA, principal component analysis, to represent the trajectory of your neuronal networks with real data, this actually is kind of magical that you can always in a small dimensional space look at the complete trajectory of networks. Actually, our work supports this idea that it should be expected. And of course, when you do the dimension reduction, you have higher order interaction. So on that, I'd like to thank you. Whoop, I'm sorry. And especially I'd like to thank Charles and Vincent. Vincent is here. We did most of the work. I also mentioned all the students that are here. Antoine presented today. Marzier and Zara are presenting poster. And Benjamin and Jordan are here relaxing and listening. Thank you very much.